Group 1 of the periodic table is a group of reactive metals. Lithium, sodium and potassium are at the top. These metals are so reactive they have to be stored under oil and need to be handled with care. Lithium is so soft it can be cut with a knife. You can see how shiny the freshly cut surface is. But leave it exposed to the air for a few seconds and it quickly begins to tarnish. It's reacting with the air. This is sodium. It's even easier to cut, and again the shiny surface soon discolours. Potassium is even softer and reacts so quickly it tarnishes immediately. Another way of comparing reactivity is to place the metals in water. Lithium floats. It reacts immediately, fizzing and skating around on the water, which is evidence that a gas is being produced. By carefully putting a tiny amount into a boiling tube, the gas can be tested with a lit splint. A squeaky pop means it's hydrogen. Universal indicator shows that at the end of the reaction, the solution is alkaline. Lithium reacts with water to form lithium hydroxide and hydrogen. So how does sodium react? Again, it floats on the water and fizzes. The gas produced is hydrogen. And the solution is alkaline. When sodium reacts with water, sodium hydroxide and hydrogen are formed. Sodium is more reactive than lithium. It's below lithium in the periodic table. Potassium is below sodium. So how would you expect potassium to behave? Potassium is definitely more reactive than sodium and lithium. It reacts immediately, and the hydrogen produced ignites on its own. Universal indicator goes blue. Potassium reacts with water to form potassium hydroxide and hydrogen. Rubidium and cesium are elements which lie below potassium in the periodic table. How would you expect rubidium and cesium to react with water? Group 7 of the periodic table is a group of non-metallic elements called the halogens. Iodine, bromine, chlorine and fluorine are very reactive, so they're not found as free elements in nature. Fluorine is a gas, but it occurs in a rock called fluorspar as crystals of calcium fluoride. This is chlorine, a poisonous pale yellow gas. The commonest chlorine compound is sodium chloride, found as rock salt and in seawater. Bromine is a dense, poisonous, reddish-brown liquid which easily vaporizes and turns into a gas. Compounds of bromine are less common, but seawater is a source of many of them. Iodine is a solid. It has the appearance of shiny grey crystals. Iodine compounds are also associated with the sea. They're found in seaweed. Fluorine is too dangerous for us to handle. To compare the reactivity of the other halogens, we can see how they each react with the same metal. This is iron wool. For it to react with iodine, it's placed above a few crystals in a boiling tube, in a fume cupboard. Heating the iodine turns it into a vapour. A Bunsen flame gets the reaction going. After several minutes of strong heating, only a small amount of the iron has reacted. It's become coated with reddish-brown iron iodide. Put bromine in the tube instead of iodine, and it immediately vaporizes. Again, the iron wool needs heating, but not as much. This time, there's an easily visible reaction. A mixture of unreacted bromine and brown iron bromide pours out of the tube. Bromine is more reactive than iodine. It's above iodine in the periodic table. Chlorine is above bromine. So how reactive will chlorine be? The apparatus on the left generates a stream of chlorine gas. Concentrated hydrochloric acid is slowly dripped onto potassium permanganate. This time the iron wool needs the slightest lick of a flame before a violent reaction races along. Clouds of pale yellow iron chloride quickly form. Chlorine is very reactive, but which halogen is the most reactive? The halogens also react with aluminium. Chlorine reacts violently with aluminium foil. It's not long before clouds of aluminium chloride leave the tube. Bromine also has a brisk reaction with aluminium foil. Iodine and aluminium powder react once a drop of water has been added. Precious metals like silver and gold are unreactive. This makes them ideal for making jewellery and ornaments. At the other end of the spectrum, metals like lithium, sodium and potassium are so reactive they can be dangerous. But there's a wide range of metals in between, and seeing how they behave in different solutions can help put them in order of reactivity. Placing the metals in lead nitrate solution provides our first clue. Silver doesn't react, and neither does copper, but magnesium and zinc both become coated with a dark grey layer of lead. Magnesium and zinc are displacing the lead from solution. Placing zinc metal in a magnesium solution and magnesium in a zinc solution will help determine which of these two is more reactive. Nothing happens to the zinc strip on the right, but magnesium reacts instantly, displacing the zinc from solution. Magnesium is the winner. It's the most reactive. But which is the least reactive? Silver is placed in a copper solution, and copper in a silver solution. The silver strip doesn't react, but the copper immediately displaces the silver. You can actually see crystals of silver growing on the copper strip. After several hours, there's so much silver it glistens, and the colourless solution is starting to go blue. So, magnesium is the most reactive and silver is the least. What would happen if you placed a strip of magnesium into a solution of silver nitrate? Chemical reactions tell us about a metal's reactivity. Mix zinc with copper oxide, lay the mixture out on a heat-proof mat, and heat one end. A reaction soon begins and spreads through the mixture without further heating. Zinc is reacting to form zinc oxide, which is yellow when hot. But what else has formed? Place the remaining solid in dilute acid, and after a few minutes, you can see pure copper. Zinc has reacted with the oxygen in the copper oxide, leaving copper behind. So zinc is more reactive than copper. Aluminium is another reactive metal. Its reaction with iron oxide gives out a huge amount of energy. A measured amount of aluminium is mixed with iron oxide and placed in a small pot. Potassium permanganate is sprinkled on top, and glycerol is added. The vigorous reaction between potassium permanganate and glycerol gives out enough heat to start the main reaction. Red-hot molten iron falls into the bucket. The aluminium has reacted with the oxygen in the iron oxide, leaving iron metal behind. So aluminium must be more reactive than iron. This reaction is so effective that it's used on a larger scale for welding iron railway tracks together. Molten iron fills the gap. And a grinder makes it smooth. Are at the top. These metals are so reactive, they have to be stored under oil and need to be handled with care. Lithium is so soft, it can be cut with a knife. You can see how shiny the freshly cut surface is. But leave it exposed to the air for a few seconds and it quickly begins to tarnish. It's reacting with the air. This is sodium. It's even easier to cut, and again the shiny surface soon discolours. 1 of the periodic table is a group of reactive metals: lithium, sodium and potassium. Potassium is even softer and reacts so quickly it tarnishes immediately. Another way of comparing reactivity is to place the metals in water. Lithium floats,